So let's go through the notes together. So we're starting off with chapter 1. What is control? Now the main thing here to see is we've got a block diagram. Notice that it's a general block diagram, can really represent anything, any kind of system which is actuating something, and a sensor. One thing to note, the difference between the desired input, which is X, and the value that the sensor reads is seen as an error, because the error is a desired value, and you take the sensor value, subtract the sensor value, and the error is the difference between the desired and the actual value through the sensor, and that error value drives the input to the system. So here's a good example of a bath. So we've got the desired value in the person's head. They desire the temperature to be a certain value, and the error signal is really 0.2 here, where it's taken the sensed value and you sense it, compare it to what you really want, what the desired value is, and the system is the actuation part of the brain which activates the muscles which turn the bath. So it's worth just having a look at these numbers and just associating them with the block diagram. And further down here we have a block diagram representation of running the bath, so it's worth just spending some time to see that. Okay, just going on to the next notes, I've got another example here of an electric fire. Note the main difference with using an electric fire over, for example, central heating. Central heating also has a sensor to feedback, but central heating tends to turn the heating element either fully on or fully off, so it's not a very good control strategy. We actually call that control strategy bang-bang control. It's either a fully on or fully off. But what we like to study in control theory is proportional control. So the sensor and the desired are giving a proportional value, and the error value is a proportional value, not just simply fully on or fully off. Now I introduce the idea of the transfer function. So the transfer function is just a nice name for that block diagram, and it basically means that the transfer function relates the input value to an output value. So here's a simple example, modelling gears. So if we have a large gear, let's say on the input it has 10 teeth, on the output it has the equivalent of 1 tooth, okay, not very feasible. Okay, let's say it's a radius of 10 centimeters and a radius of 1 centimeter on the output, so we'll ignore the teeth, we'll count it in distance instead. And if I rotate the input shaft 1 revolution, the output shaft will rotate 10 revolutions, so the transfer function of the gears for position would be 10 to 1 in this particular case. Now, just looking at figure 6, here's a really important point. Transfer functions don't have units, and it depends what you're looking at. You know, it depends what the input is and what the output is. So for example, for the same setup of gears of 10 to 1, if we're looking at torque, you probably realise that the torque would be 1/10. So if the input value is a value of 1 on the torque ratio, the output would be 1/10 of that. So it really does depend on whether you're looking at position or torque, sometimes velocity. Let's look at another example, modelling the spring. So within springs they have a certain stiffness factor, and we call that the K factor. So the K is how is the distance of a spring related to the force, and you can see a transfer function here of force in. We've got the spring value, which is the 1 over K, and that's in respect to the displacement. Moving along to the potentiometer, a potentiometer is just also known as a variable resistor. You turn the input and you get a voltage on the output when it's connected properly in an electronic circuit. And the transfer function for this is Vs, which represents the voltage supply, divided by 2 pi. Now I've put 2 pi because 2 pi is 1 complete revolution in radians. So if it was 1 complete revolution, it would be 2 pi radians. So we would have an input of 2 pi. 2 pi multiplied by Vs divided by 2 pi. 2 pi divided by 2 pi would cancel out, so the output would be Vs. And if the revolution was 0 radians, it would have 0 times this, so the output voltage would be 0. So have a think about what would happen if I turned it halfway. So if the input was just pi radians, what would the output voltage be? Now, just looking at the motor, what we're looking at here is that there's a lag in motors, and we'll come to that a bit later on in the course. But with a motor, you've got voltage in and you've got speed out. And in control, as I mentioned previously, we measured angle in radians. Well, speed we measure in radians per second. Looking at the electric motor and feedback, I'm looking at voltage in, and we have the motor, and what I want to do is measure position. Now you might notice this integrator block here. So what's going on there? Well, if I put a voltage into a motor, I would tend to get a varying speed out. But if I want to measure position, I would have to integrate that speed and then find the value of position. And that position value could then be fed back in the terms of, for example, a potentiometer, which would affect the desired input position of the motor. So I've got a few things for you to think about here, and what I'd like you to do is draw block diagrams of these systems that I'm asking you to think about. And just down below there's an excellent link. If you follow that link and follow the first two experiments, E1 and E2, you can have a play with things like time constants. Like I say, we will cover it a bit later on, and get a bit more of a feel for things like step responses. Thank you.